So in this video, we're going to use separation of variables to do a Newton's law of cooling problem. So the example here says a metal tube whose temperature is 300 degrees Fahrenheit is placed in a room whose temperature is kept at a constant 70 degrees Fahrenheit. 5 minutes later, the tube has cooled to 200 degrees Fahrenheit, and it says use Newton's law of cooling to determine or to develop, there's a typo right there, to develop a model for the temperature of the tube. So Newton's law of cooling is pretty straightforward. Newton's law of cooling says that the rate of change of the temperature, so if we let little t be time and capital T be temperature, then Newton's law of cooling says that the rate of change of the temperature, d big T, d little t, in other words, T prime, the rate of change of the temperature, is proportional to the difference between the current temperature, T, whatever that is, that's changing with respect to time. So the rate of change of temperature is proportional to the temperature minus the ambient temperature that the object that is heating or cooling is in. So the ambient temperature could be the temperature of a room that's climate controlled. It could be the constant temperature of an oven. It could be the constant temperature inside of a forge. So if we have a constant temperature, then the rate of change of temperature is proportional to the current temperature minus the temperature of the environment in which the thing is heating or cooling. So in this case, we're given some information about the object that's cooling down. So we have a metal tube. It's 300 degrees Fahrenheit and it's placed into a room. And the moment it's placed into a room, it's going to start cooling and it's going to try to approach the temperature of the room over time. So we're being told that the temperature at time equals 0 is 300 degrees Fahrenheit. We're told that it's placed into a room that has a constant temperature of 70 degrees. We're being told that the ambient temperature in which the tube is residing is 70 degrees Fahrenheit. We're told that 5 minutes after it's placed in the room, the tube is cooled. So we're being told that T of 5 is equal to 200 degrees Fahrenheit. So I think we've pulled everything from here that we can get. So notice that T sub A can be replaced with the 70 at any point in the solution process. We can do it any time that we want to. So the first step would be to separate variables. So I could multiply both sides by dt, which would give me d big T equals k t minus t sub a times d little t. And I haven't separated variables yet because d big T is over here, and here I have the variable big T sitting right here. T sub a isn't a variable, it's just a constant. It's the ambient temperature. So what I'm going to do next is multiply both sides by 1 over T minus T sub a. So on the left hand side we'd get 1 over T minus T sub a d big T equals the k dt. So that's by algebra. And then once we've done this, we see that we've separated the variables. Everything with the big T is with the d big T, and everything with the little t, which is nothing, is over here with d little t. So then once we do that, we're ready to integrate both sides. So we integrate both sides and we get plus a constant of integration. And this is 1 over crap, so we're going to guess that the derivative is the natural log of the crap. So natural log of T minus temperature ambient. And to check our work on that, we could take the derivative of this. We'd get 1 over the stuff times the derivative of the stuff, but only the t is the variable, so the coefficient on the t is a 1, so we'd get the derivative of t minus t sub a is 1, which is exactly what we have in the numerator. So that checks out. So we get equals, and the antiderivative of k dt is just going to be k times t plus our constant of integration. And now we'll make both sides an exponent on base e, so we get e to the natural log will give us T minus temperature ambient, and then we'll have e to the kt plus c. And like we've already seen in previous videos, if we have the sum of two expressions in the exponent position, we can rewrite this as a product. So e to the kt times e to the c, because when we multiply the same base, we add the exponents, and then e to the c is just itself a constant, so we can replace that with a constant, and then the convention is to write that in the coefficient position on the e to the kt. And we do want to solve for t, so notice we could just add the ambient temperature to both sides at this step. So we get e to the kt plus t sub a, and then our job is to put the correct value in for t sub a, to solve for the constant of integration, and to solve for the constant of proportionality. Those are the three pieces that are left. To me, taking this guy right here without solving for the t sub a is convenient for solving for both c and k. So I would, at this point, before I even fussed with writing it in this form, I would look at this t minus t sub a equals c e to the k times t, and I would go ahead and attack trying to find c and k at this point. So that's just a matter of plugging in these conditions right here. We've been given two conditions, which is good because we have two unknowns to solve for. So this first one says that when big T, when temperature right here is 300 minus our ambient temperature, which we know is 70, that this equals c times e to the k times 0, because we replace little t with 0. T of 0 equals 300, replace big T with 300, little t with 0. 0 times k is 0. E to the 0 is 1, so we just get that the constant is going to be the difference between the initial temperature and the ambient temperature. So we get 300 minus 70 is 230 equals that constant. And then we can step back up. Once we've solved for this, we can update the model with that value. So we have T minus T sub A, the ambient temperature, equaling 230 e to the k times t, and then we take the second piece of information, the piece right here, and we plug in 5 minutes and 200 degrees Fahrenheit, so we get 200 degrees Fahrenheit minus that ambient temperature of 70 degrees equals 230 times e to the k times time is 5. So we get 200 minus 70. 200 minus 70, that's a 130. We then divide both sides by 230 to get the e by itself. So we get 130 over 230 equals e to the k times 5. And then to get the stuff out of the exponent position, we take the natural log of both sides. So we get the natural log of 130 over 230 equaling the natural log of e to the k times 5. And the natural log base e cancels exponential base e. So we just get a k times 5 right here, and this is the natural log of 130 over 230, and then multiply both sides by a fifth to solve for k, and then we go and just update our model right here. So our final model is going to be temperature equals c, which we determined was 230, so we get 230 e to the k, but k is just 1/5 the natural log of 130 over 230 times time plus the ambient temperature, which is 70 degrees. So there's the final model. And in general in the homework, what I don't want is for you to use a formula to work with Newton's law of cooling. I want to see you work through the differential equation from scratch, starting out with, so in the homework I want you to start out with the idea that the rate of change of the temperature is proportional to the difference between the temperature and the ambient temperature. And I want to see you work through from scratch in homework assignments, because it's a differential equations course. It's not a use the formula course.